Alright, so in this tutorial, what we want to do is transition from this matter to energy phenomenon, which I said that more than anything occurs at a nuclear level, even though we focused on an odd process called annihilation. And now we're going to turn our attention to the nucleus and establish some basics. Stuff should be very familiar to us, but then we're going to turn our attention back towards turning mass and energy and figuring out how much you get for a particular process. This will set us up for understanding two very important nuclear processes, nuclear fission and nuclear fusion. So we're going to try to get through just this one page right now, establish some very basic concepts, and introduce the atomic mass unit and how it can be used as a convenient way of expressing atomic masses and the like. Okay, so let's do just something that hopefully is familiar to us, maybe we've forgotten. How we represent the key parameters of a nucleus. So in this diagram we have an aluminum nucleus, okay, and I'm just going to rewrite it over here. So we of course put the chemical symbol for that, and then just a reminder of the two relevant numbers for a nucleus. Okay, so this is right here the atomic number, which is given the symbol Z. So atomic number is given Z in our equations, and it is simply the number of protons in the nucleus. This number right here is the atomic mass, and that's given a symbol, capital A. I don't know why, but that's just the way it is. And then we know from chemistry that there's a relationship between atomic number and atomic mass. They're different because the mass reflects the number of protons and the number of neutrons. So capital N is given the number of neutrons, and that is simply equal to the mass minus the number of protons, or the atomic number. So N equals A minus Z is something to keep in mind, but then again, you kind of know that already. And this sums it up nicely right there. Okay, so very often we are interested in the number of protons and neutrons for a nuclear reaction because that really is a reflection of the mass. But it's not convenient to express those masses in kilograms, which we would need for E equals mc squared. So we're going to learn how to figure out the amount of energy you get for certain nuclear processes based on a new unit of mass called the atomic mass unit. AMU, or U for short, for universal atomic mass units. Okay, so we're going to define what it is and then, again, how to convert that to energy. So the definition of an atomic mass unit is 1/12, exactly 1/12, the mass of a carbon atom. Why carbon? It's a fairly standard atom, very abundant, and that 12 is a nice number. Okay, so 1 U is also equal to a certain number of kilograms. And you don't have to know this, but I'm going to put it here because it's going to be relevant. It's about 1.66 times 10 to the negative 27 kilograms. It's almost exactly the mass of a proton. It's just slightly less. Okay, so what we want to do here is how much energy do we get if we were to take 1 U of mass and annihilate it, let's say. We don't worry about what process would do that. It's not like it would meet an anti-U, but it would be equivalent, I guess, if you will, of a proton meeting an antiproton. So to do that, if we want energy equivalent, we've seen already that the energy is equal to the amount of mass that is destroyed times the speed of light squared. So in this case, we would have to put the mass in kilograms because we want to get their answer in joules. So we take what 1 U is, 1.66 times 10 to the negative 27th, multiply it by c squared, which of course is 3 times 10 to the 8th squared. And I'll trust you to do the math, and that turns out to be about 1.5 times 10 to the negative 10th joules. Okay, that's actually a fairly decent amount, but it's still pretty tiny. So now what we want to do is, since this is such a tiny amount of energy, we want to go to our more convenient unit of energy called the electron volt. And if you recall, 1 electron volt is 10 to the negative 19 joules. We can convert this number right here into electron volts. And again, that's pretty straightforward. So if we do the maths, we take the number of joules and we divide by 1.6 times 10 to the negative 19. Maybe I should show that. So the number of EVs, actually, I'm going to do our old-fashioned table. So the number that I want to convert is this. okay, over 1. And then I'm going to do here, and I'm going to take my conversion factor. I'm going to put joules on bottom so that the joules cancel out. And that's equivalent to 1 electron volt. So if I divide those two numbers, I get 9.31 times 10 to the 8th electron volts. So it's quite a few. 900 million electron volts are associated with the mass of essentially one proton or one atomic mass unit. So rather than leave it as 9.31 times 10 to the 8th, we're going to put a prefix in there. This is a large number. We're going to convert this to MeV, mega electron volts. And if you recall, mega is 10 to the 6th. So if I do the conversions, we see that's 931 MeV. So this is a very, very important little conversion, that if you have a change in mass of a nucleus or some nuclear process that's equivalent to 1U, you're going to get 931 MeV of energy. That corresponds to 10 to the negative 10th joules, but when we start looking at nuclear processes, we're going to start expressing many of our masses in these terms, so it's a convenient form of comparison. All right, so let's do one little problem and we'll end this tutorial around 10 minutes. So let's look at something called binding energy. It's going to be a very important concept. Let's take a helium atom. Okay, so a helium atom with this nomenclature here, with the symbols here, He24, we can deduce that it consists of 2 protons, because the atomic number is 2. Since it's a neutral atom, the number of electrons has to be the same, so the 2 electrons. And since the mass is 4, and we have an atomic number of 2, then the number of electrons is 2. Okay? So that should be standard for you for any situation. Now, what you wouldn't know off the top of your head is what are the respective masses of each particle. So the mass for an electron is given in terms of U's right here, and the proton and the neutron. Notice that the proton and neutron are very, very similar, but the proton or the neutron is a slightly higher mass when you go out to about the 5th decimal place. And if you add the mass of the proton and the electron, it's very, very similar to the neutron. But that's all right. So let's figure out what the combined mass is for all the particles that make up the helium atom. Okay, so that would be really 2 times the mass of an electron plus 2 times the mass of a proton plus 2 times the mass of a neutron based on what we saw before here. So let's pull out the 2. So that's going to be 2 times, now this is kind of tedious, 0.000549 plus 1.007276 plus 1.007825 U's. Okay, so we'll get out the calculator, and when we add up the terms in the parentheses and multiply by 2, we get a total mass of 4.03130 atomic mass units. Okay, so you're wondering, why are we doing this? Well, if you look at the actual nucleus or the atom of helium, we find that the mass is only 4.02603. It's less than the sum of its parts. So what we have to be able to do is explain why the overall mass of the helium atom is less than the constituent parts. Okay, in other words, what accounts for this mass defect, which is given a symbol delta M. Okay, well, if you haven't figured out already, the mass defect represents something called the binding energy needed to hold the atom together. Okay, so let's think about this. If we have 2 protons come together to meld with 2 neutrons to form a nucleus and then bound to their 2 electrons, what happens is a lot of that mass, a significant chunk, which we'll calculate in a little bit, goes towards an energy given up so that the nucleus is bound together, and if you want to separate it, you need to input a decent amount of energy, the amount of energy that was given up. And almost all this energy is due to the nucleus. Very little of the binding energy is due to the electron part of it, but we include it just to be thorough. Okay, and the reason we need this binding energy is because what you're doing is you're cramming all these protons, or in this case just 2 protons, in a very, very, very small space. They want to repel each other, so you need that energy to overcome the Coulomb repulsion that comes from putting positives in a very, very, very small space. Okay, so we want to understand then, if there is a difference in mass between the constituents and the whole, how much energy was lost. In other words, or how much energy was given up by this loss in mass. So that's where our MeV conversion factor is going to come in very, very handy. So let's first of all calculate the mass defect. So the mass defect is the difference in mass between the products and the overall atom and the individual part. So our overall individual parts we saw earlier by calculation was 4.03130, and the mass of a nucleus, or excuse me, a helium atom is 4.002603 U's, right? So remember, we're in atomic mass units. So get out the calculator. Okay, and when we punch in the numbers, we see that the mass defect is a very, very small amount, 0.028697 atomic mass units. Okay, so anytime in some process, and this would have occurred most likely during the Big Bang, okay, that the 2 helium, or actually not only the Big Bang, but inside stars, right, this is what's going on very often in fusion or some form of this, is that the loss of mass is small, and that corresponds to a certain amount of energy. So the energy that we have is still mc squared, but we can't use this form because m is not in kilograms. So I can't stick in 0.028 U's multiplied by c squared to get the energy. It wouldn't work out. So what I do instead is I use the idea that 1 U of mass is equivalent to 931 MeV of energy. Okay, that was the whole point of that conversion we did earlier. So in this case, we have 0.028697 U's were lost, and that's going to be equivalent to 931 times that. So if we do the math, that's 26.7, and I'll just round it off there, MeV of energy. Okay, now that's not a whole lot of energy, but that's just for one formation of, or one nucleus or atom. You do that for many, and you see that the energy builds up very, very quickly. Okay, so there's our introduction to the atomic mass unit and how it can be used to look at losses in mass when we, let's say, form nuclei. Then we're going to look at what happens when you split nuclei or do something similar with fission and fusion.